excitation in BC. BC gives a wealth of topological excitations. Examples include Dirac monopole, the vortex molecule, knot excitation, and the Kibble-Zurich mechanism. By way of introduction, let me start by discussing where we should look for new phenomena in ultra-cold atomic systems. One is that the system is extremely dilute, with atomic density 5 orders of magnitude more dilute than that of air. This implies a very long collision time of the order of milliseconds, and the kinetics becomes very important. For example, 1 millisecond is a time for an atom to go around a track before colliding a second collision. Therefore, the dynamics of phase transition and defect nucleation can be investigated in real time. For example, this panel shows the vortex creation. Initially symmetric BC spontaneously breaks its axis symmetry and eventually form a triangular lattice. The color shows the phase of BC, which can also be plotted. The right panel shows the phase dynamics of spinor BC. The right panel shows the phase. Left panel shows transverse magnetization. As time progresses, we see here and there blue dots, which shows spin vortices. So this could be used as a test of Kibble-Zurich mechanism. And the second feature is that the energy and angular momentum of systems are conserved. In condensed matter systems, energy and angular momentum are not conserved in general. So we look for the ground state for the phase diagram. But in this system, both energy and angular momentum are usually conserved. And this conservation imposes special constraints on the time evolution of the system, leading to, for example, spontaneous structure formation. For example, this panel shows a elongated ferromagnetic BC. Initially, all atoms are prepared in the magnetic sublevel M equals 0. Due to spin conservation, as time passes, this kind of domain structure are formed, and eventually we have this helix of spin textures. So this is also due to the spin conservation and energy conservation of the system. So we can look for those unique structure formation in this system. And third, the spin exchange and the magnetic dipole-dipole interaction play a crucial role in determining magnetism, spin texture, and topological excitation. What makes the system cornucopia of symmetry breaking is the fact that the system involves energy scale over 5 orders of magnitude. By far the largest is the Zeeman energy, which causes the spin precession of the atomic system. The largest energy scale beside this is spin-independent Hartree interaction, which together with a trapping potential determines the density distribution of particles. 3 orders magnitude smaller than this is spin-dependent interaction. Alkaline atoms have spin. When they collide in a spin parallel or anti-parallel manner, has slightly different energy of the order of 1 nanokelvin. And this slight energy difference gives rise to the magnetism or the order parameter, spinor order parameter. By far the smallest is the magnetic dipole-dipole interactions. But nevertheless, this interaction plays a dominant role in determining spin texture, that which is the spatial distribution of spin orientation. The crucial question is that the temperature is around this, usually. So why can't these very small, much smaller than temperature, nanokelvin physics be observed at microkelvin temperature of the system? The answer is the botonic stimulation. So once the system undergoes BC, all both condensed atoms respond to an external perturbation in exactly the same manner. For example, dipole-dipole interaction for rubidium is 0.1 nanokelvin, and for chromium is 10 nanokelvin. But when they undergo Bose-Einstein condensation, the collective energy amounts to 1 microkelvin for rubidium and 100 microkelvin for chromium. Therefore, we cannot ignore those tiny dipole effects when considering the dynamics longer than 100 milliseconds for rubidium and 1 millisecond for chromium, which is determined by the time energy uncertainty. The system involves various types of topological excitation, like U1 spin structure, non-abelian vortices, monopoles, Dirac monopoles, various types of skyrmions, and node excitations. Many of these topological objects can be created experimentally and probed in a visualized manner in atomic gas BC. And those visualizations, as I showed a few examples, stimulates our imagination, fostering further developments. There are three distinct features of atomic gas BC. First, the system has electronic rather than nuclear spin. Magnetic moment arises primarily from electronic rather than nuclear spin, which allows local manipulation of spin textures. In contrast, in superfluid helium-3, local manipulation of spin texture is impossible because magnetic moment originates from nuclear spin, which is too small. So therefore, in superfluid helium-3, we can manipulate D vector only via the L vector. But in this system, we can manipulate local spin via the local magnetic field. So this has a great advantage in terms of manipulation of the system. Second, the system possesses spin gauge symmetry, which couples superconducting spin textures. Suppose, for example, the case of spin 1 BC, rubidium BC. When all spins are aligned in the same direction, the order parameter is 1, 0, 0. This is a magnetic sublevel. All spins are up. General order parameter can be obtained by rotating this order parameter via the Eulerian angle, Eulerian direction, multiplied by gauge transformation. The crucial observation is that this is a general order parameter which involves gauge phi and rotation angle gamma as a linear combination. This implies that if you rotate the spin locally, then the system will try to undo it by flowing supercurrent. The local frustration of spin gives rise to supercurrent and vice versa.
Excuse me, is gamma the rotation about the direction of the spin, or
yes, yes.
Or
about
is it
about around the direction of the spin?
Okay.
And this symmetry can be used to convert, for example, synthetic gauge field, Bailey phase, etc., to supercurrent, and vice versa. And again, the ability of locally manipulated spin gives us a great opportunity to manipulate the system. And in contrast, superfluid helium-3 has an orbital gauge symmetry rather than spin gauge. And third, the system has discrete symmetry rather than, in addition to this spin gauge symmetry, the system has discrete symmetry. For example, spin 1 BC has 3 phases: ferromagnetic, polar phase, and what is called Rosner symmetry phase. And ferromagnetic phase has a U1 symmetry, but polar phase has a 2-fold symmetry. Spin 2 BC has several phases: ferromagnetic, cyclic phase, and nematic phases. This looks like a liquid crystal phase. And all phase has distinct discrete symmetries. And these discrete symmetries combined with this spin gauge symmetry leads to the fractional vortices and non-ambient vortices, which I will describe later. This panel shows the order parameter manifold and the homotopy group for typical systems. This is superfluid helium-4, which has a U1 symmetry and a simple ordinary vortex. And this is superfluid helium-3, A phase and B phase, dipole low and dipole free phases, which has a very rich order parameter manifold. Therefore, this system can hold a very rich topological objects. In this box shows a spinor BC case, which has also very rich and distinct phases from superposition helium 4. For example, if we call spin 1 or spin 2 ferromagnetic BC can host SO3 vortex, Dirac monopole, and Shankar scan. Spin 1 polar phase, this is a rubidium, and this is a sodium BC, can host a half quantum vortex, two-Polakov monopole, and Notz excitation. And even more interesting is the case of spin 2 biaxial nematic and cyclic phase. This can be realized for rubidium 87 BC. In this case, order parameter manifold has a quaternion symmetry and a tetrahedron symmetry. And those order parameter manifold can host a non-abelian vortices. So we can study a very rich variety of topological excitations. So what's the topology of a quantized vortex? Well, the topological nature of a quantized vortex can be understood by looking at how the order parameter changes as we make a complete circuit of the vortex. For example, the scalar BC and the superposition helium 4 has a scalar phase. And single valuedness of the order parameter dictates that fundamental units of vortex is 2 pi. This is an integer vortex. Spin 1 polar phase, which is a sodium BC, has this two-fold symmetry. Polar phase is a phase in which all bosons reside in the m equals 0 state. So this is a non-magnetic state. And the order parameter is a gauge factor multiplied by spherical harmonic L equals 1, M equals 0, which is a cosine theta. Since cosine theta has a two-fold symmetry with phases 0 and pi. So this system has a discrete symmetry. Suppose that we rotate this order parameter upside down as we make a complete circuit of the loop. Then 0 phase lobe turn into pi phase lobe, pi phase lobe turn into 0 phase lobe. Single valuedness of the order parameter is met by an additional gauge transformation by pi, because pi has already been taken into account by this discrete symmetry. And since pi is 1/2 of 2 pi, so this system can host a half quantum vortex. As we have seen from a previous talk, there's a very interesting ruthenium case. In that case, this two-fold symmetry arises from orbital. Here it arises from spin. The spin 2 BC now has a very unique phase, which is called cyclic phase. And in this phase, 3 bosons form a spin singlet trio, and this trio singlet undergo BC. Note that this spin singlet trio is impossible for spin 1 case, because Bose symmetry dictates that 1 plus 1 gives 0 or 2. Addition of another 1 spin atom doesn't give rise to 0. But for the case of spin 2, 2 plus 2 give rise to 0, 2, or 4. If it's 2, then addition of an extra atom gives rise to 0. 2 plus 2 is 2, then another 2 gives rise to 0. So this trio singlet is unique to spin 2 BC, and order parameter looks like this. So it has a tetrahedron symmetry with 3 lobes, featuring phase 0, 2 pi over 3, and 4 pi over 3. Now suppose that as we make a complete circuit of a loop, we rotate this lobe by 2 pi over 3 around 111 axis. Then this 0 phase turn into 2 pi over 3, 2 pi over 3 lobe turn into 4 pi over 3. Therefore, the single valuedness of the order parameter is met by an additional gauge transformation of 2 pi over 3 or 4 pi over 3. Therefore, this fundamental unit of this vortex system is 1/3 or 2/3. Okay, now let me discuss abelian versus non-abelian vortices. scalar BC and superfluid helium-4 has integer phase, and spin-1 polar BC and superfluid helium-3 A phase has a half contact vortex. All these states have only one rotation axis, that is SO2 rotation. Since two rotation about the same axis commute, vortices created in these systems are available. However, as I discussed, spin-2 cyclic phase has many rotation axes. There are actually 12 rotation axes corresponding to SO3 rotation. Since two rotation around two different axes do not commute in general, vortices created in this system is non-abelian. Non-abelian vortices give rise to very interesting possibility in terms of collision dynamics. When two vortices collide, there are three possibilities. They reconnect, they form a run that bridges two vortices, or they simply pass through each other. For abelian vortices belonging to the same species, like two vortices from the same BC, all three processes are topologically allowed, but energetically most favorable one is reconnection. Therefore, in superfluid helium-4, when two vortices collide, usually they reconnect. And this reconnection
dynamically, because I'm used to thinking that reconnection is something which happens that naturally happens dynamically. Because when you just have vortex reconnecting, it's a classical problem, classical hydrodynamic problem. Then you have just forces which pull them apart. So
yes.
The matter of energy, the energy is conserved.
Energy is conserved. But actually, I will show later that dynamically other cases could also happen, depending on whether they belong to the same species or different species.
I'm just saying of single component.
Single component case.
It's well established numerically that vortices in a single, say, just in thinking like Ross-Petayevsky, they always reconnect when they cross each other.
No.
I disagree with this.
There are some literature. Depending on your initial kinematics, even, for example, this run formation, run is formed. There are actually, we can show by direct numerical simulation.
Yeah, but I was just commenting on the single component case.
The single component case, yes.
Huh?
Yes. But I agree that naturally, in a very natural configuration, most of the case, this is dynamically fluid. Not just energetically, but also dynamically. But this could also happen. For abelian vortices belonging to different species, for example, rubidium Fe called two-component rubidium systems. Okay, one vortex from one BC, one vortex from other BC. Then all three processes are also topologically allowed, but energetically most favorable one is passing through, and also dynamically favorable. But non-abelian cases, passing through and reconnection are topologically forbidden. Because suppose that A and B are generators of vortices. By definition, non-abelian vortices means that commutation relation between A and B do not commute. Therefore, this configuration and this configuration has a difference that depends on the commutation relation between A and B. When they do not vanish, then they naturally form a run, which is generated by the remnant commutation relation between A and B. This partly shows that numerical simulation. For non-abelian case, when they collide, they form a round structure and they never detach each other. But for abelian vortices, when they collide, they simply recombine. So this is dynamical concept as I mentioned. And it's interesting that this looks like a vortex confinement, okay. Like a QCD. When they collide, when QCD, pion collision.
Excuse me, but what's plotted on the colors? I mean, this is vortex core presumed for this abelian vortices, but what's the blue color? Is it non-abelian vortices?
That's a 1/2 vortex. Yeah. So initially this is 1,000 vortex. They collide, then the different species of vortex, 1,000 vortex. So the color refers to different species of vortex. And this one shows origin dynamics of pair vortex field. When two same species vortex collide, when they fuse into a same vortex. So the same species fusion occurs.
So, can I ask you a more technical question concerning the previous slide? So we know when two vortices reconnect, 2 billion vortices reconnect, they always produce Kelvin waves, and this is similar. When they will reconnect, you will see that there will be waves, precession waves on the vortices, just running away from the point of reconnection. Do you have the same phenomenon with non-abelian vortices, like waves? So despite the fact that they do not go away from each other, do you see these waves propagating away from the reconnection?
Some waves.
Because it's in the case of abelian vortices, the main relaxation mechanism for superfluid turbulence, which I will discuss.
Yes.
I wonder whether you have the same mechanism in non-abelian vortices.
Well, that again depends on the initial condition. But when we collide two vortices at a very high speed,
that's what I not quite understand, because in my opinion, just locally, these are just two straight lines. Am I right that locally, if we have a parameter like the vortex core is much smaller than the intervortex separation, I don't care about the ends. I just see two almost straight lines. And then the velocity is controlled, I believe, by just equation of motion, like Kelvin's theorem in the case of abelian vortex events. Or probably some equivalent. So my point is that the velocity at which the guys collide is a function of just the geometry, like curvature.
Geometry.
It's not a free parameter. How can you control the velocity of collision?
Oh well, that's numerical simulation. So when we collide, then we prepare initial two configuration.
Right. But
And then we give initial velocity.
wait a minute. But your equation is the first order differential equation, right? Like Gross-Petrievsky. Meaning that you can prepare only a static configuration. What is the first order differential equation as opposed to second order? You do not have velocity as your initial parameter. You have only static configuration, and then you apply your first order differential equation to evolve.
Oh, what do you mean by static?
Static, I mean that we all know that in the first order differential equations with respect to time,
Okay.
it's only this initial configuration, static in initial configuration, which matters, because the rest, you see, you do not have velocities. The velocity will be prescribed by time evolution. You cannot use velocity as a free parameter.
Okay. Well, I think by velocity, I mean it's a euphemism. But still, I see some velocity.
Oh yes, it's given by the Kelvin's theorem, by the curvature of the vortex. So if it's curved, it moves. If it's straight, it doesn't move.
What we actually give is an initial static condition.
Perfect. Yes. And you mean that depending on this condition, you see different effects? Yes.
Now these dynamics in a track or in a box?
In the box. In the box, periodic function. Okay. So we discussed the left-hand side. And now the middle one is a case for those two vortices belong to different species. And when they collide, then according to the law, as I said, they simply pass through each other. Because they
different species.
Different species.
Oh, because they can. I see.
And the right part shows no ability.
Well, probably then I simply missed your point, because you were saying that just different species can pass through each other, because I was thinking of just single species,
Oh, okay.
which cannot.
Which can.
Do you agree with me? Okay, we're on the same page.
Okay, so for the case, for no-ability case, we have a structure. Now, what does this imply? I think it has a direct implication on quantum topics. Because for the non-abelian vortices, as we saw, collision dynamics are highly non-trivial. For the case of abelian vortices, self-similar Richardson cascade processes based on reconnection based on the famous Coulomb process. So So initially large vortices collide, and the scale goes down to a smaller and smaller. This gives rise to the famous origin.
It's a wrong picture.
Oh, very interesting.
Yes,
So,
tomorrow I will explain it. It was Feynman's idea of 55, it's wrong. Vortex cannot just have a cascade, or a ring cannot have a cascade decay into smaller rings by conservation of energy moment. It's all different. But tomorrow I will tell you this stuff.
okay, I'm good. But for non-abelian case, we have network. So rather than vortices go into a smaller scale, we expect a large structure growth by this run formation. Okay, so this panel shows the numerical simulation. The left panel shows abelian case. I do see incorrection.
These are larger rings, they're not smaller rings, because in that Feynman type cascade, a single ring was supposed to experience a cascade of decay, say 1 into 2, and smaller ones go into smaller and smaller and smaller. Yes. It's like a single, you take a single ring, and basically Feynman's idea was that the rest is not important, like a single ring keeps decaying into smaller ones. And if, because the rings do play a role, at a certain scale, but not in a trivial way, like a single one that decays in a period. An interaction with the rest of the tangle is important. I will tell you this story.
Okay.
The crucial point is the Kelvin wave cascade. The main inertial range is due to Kelvin waves, which I was mentioning. Just the waves on the vortex line. So this is the main type of the cascade process which is responsible for the decay. So when the guys reconnect, they create Kelvin waves, and these Kelvin waves cascade. And this scenario does apply to non-abelian vortices, because if you do create these Kelvin waves, this scenario can be universal for both abelian and non-abelian. Because the distortion waves can cascade, so the tangle gets more and more dilute, and the energy is taken by these distortion waves propagating along the lines.
So according to your theory, Kolmogorov law comes from what?
Oh, Kolmogorov is different. Kolmogorov law, here you will not see the Kolmogorov, because it's so-called violent turbulence when you have a chaos. In this case, you will never have a Kolmogorov law. To have a Kolmogorov law, you need a polarized tangle, because how superfluid cannot rotate, but it can mimic rotation. It mimics rotation by head, we will know how, right? By an array of parallel vortices. So Kolmogorov turbulence is all about rotation. So locally, you need an array of parallel vortex lines. So Kolmogorov, in superfluid turbulence, we have two different regimes. This regime is called Binance regime, and we have a chaos like that. And we have a Kolmogorov, if you stir superfluid, then instead of this absolutely chaotic tangle, you would have a tangle consisting of locally parallel lines. So there will be a sort of local order of lines. And by doing that, the superfluid would mimic the rotation of classical fluid at large enough scale.
But I do see Kolmogorov for this.
This, that's strange.
Yeah,
So
what is
what was your starting point for this simulation?
Yeah. it's a good
Was it
question.
was it one long string, or was it many random strings?
Three.
One long. Was that?
No, three.
No, when you started this numerical simulation,
Yes.
what was your initial value? Was that one long vortex, or
No.
was it many?
Several.
Several. Okay. What would happen if you start with one long? Because that relates to this question.
Yeah, I haven't.
You see, probably you see this quasi-Kolmogorov regime, not in the whole inertial range, but I don't know, maybe half a decade, something like that. You see, I'm talking of a really serious Kolmogorov regime, which takes, I know, at least 1 or 2 decades, something with a really large inertial range. If you see something like Kolmogorov in a very narrow range, okay.
Yeah, in this case, I have done it's narrow.
Yes, that's the point. That's the point. You cannot have an extended Kolmogorov
Right.
regime, taking it from one scale to, say, a scale which is by a factor of 10
Only
small.
for limited.
Yes. If it's just, I don't know, half a decade, it's not the Kolmogorov. It's something I had quasi.
Quasi.
I'm talking of a really extended inertial range. in which case you need this polarized tag.
But that's hard to obtain.
People did see more than 10 years ago. Norway and collaborators seen it, I believe in 1908 or something like that, maybe yeah, 20, or maybe even earlier, maybe 98.
So the question is what would happen for non-abelian case. And so this puzzle shows some preliminary example. So initially, 1/3 vortex shown in blue are prepared, and as the system evolves according to velocity, we see here their green and red run, which shows 1/2 and -1/3 vortex. So non-abelian vortices collide and form two types of runs in this case. And so about Kolmogorov. What we did is just to calculate the total vortex time legs as a function. And we did compare this case and this case, abelian versus non. And for abelian case, we will see Kolmogorov type power. In this case, it again obeys a power law, but different power. And it's remarkably long. This is really preliminary, so I am not in a position to make a deep analysis. But turbulence with no abelian vortex doesn't seem to have turbulence. Okay, now let me turn to the question of knots in a spinor BC. Knots has a very long history from ancient times, Asian knots and mathematics and also chemistry. But knots have been also very popular in high energy fields as an effective low energy excitation, QCD. But experimentally there is. But knots can be created in probe in a spinor BC quite easily. So in spinor BC, there are many proposals for topological excitation, fractional vortices, monopoles, and scramblings. These topological objects are all characterized by winding number. In contrast, knots are characterized by the linking number. What's the linking number? Linking number is a number of times two field loop link. Suppose that this is a BC, spinor BC. And suppose that we form, we make a trace in which local spin orient in this specified direction, and we take another trace in which local spin orient in a different direction. If they link once, then the linking number is 1. Now, how to create knots experimentally? Well, without going into detail, let me tell you how. So hold your polar BC. For example, if we call one sodium BC in optical trap, subject to a quadrupolar magnetic field, and wait just for 10 milliseconds. Then you will get. The basic idea is to apply the quadrupolar magnetic field, and by using this quadrupolar magnetic field, we rotate spin locally. Then not like spin texture is formed. This panel shows the dynamical simulation. So this is BC. Then one after another node comes into from the periphery as we on the order of 10 minutes. The parameter we use is just as normal as used in the experiments.
Sorry, what's the colors here on this?
Colors show the direction of spin. So for example, this color shows X direction, this color shows Z direction. So because of the quadrupolar magnetic field, local spin direction rotate in time. As they rotate in time, those rings enter this. Now, how to probe this node? After 3 milliseconds, slice the BC as done by an MIT group and perform Stern-Gerlach experiment. Then if there is a knot with linking number 1, then we have a double ring structure in any spin component, m equals 0, m equals 1. So this is a smoking gun. If there are 2 knots, then we have 4 rings in any spin component. Okay, so finally, let me discuss.
Basically, this system knows they are something dynamical, so there is no way to they would want to shrink, right? Always.
Eventually, yes.
Yeah.
Yeah, no stabilization, unlike Fadev's original idea.
But I mean, there are many kinds of knots. Is this just the linking of 2? That's what you call the knot here.
Actually, so far we have found only this type. Yeah, and currently we are trying to make, for example, threefold, starting from other initial conditions. So far unsuccessful. So I think it's a very interesting subject to look for another initial condition so that we can create other type of modes. There are many other type of modes. So far, what we have found is only this type. This is called unknown because it's trivial. Okay. So finally, let me discuss what we call vortex tiling problem. So vortex core is a singularity of the order problem. So the scalar BC, since there is only one component, so the vortex core has to be empty. But spin 1 BC has 2 possibilities, ferromagnetic or polar. It turned out that vortex core of a ferromagnetic BC is filled by a polar phase rather than vacuum. And vice versa, vortex core of a polar BC is filled by ferromagnetic phase rather than empty. So spin 1 case vortex core is non-singular, filled by other phases. An interesting question arises for spin 2 BC because in this case the ground state has at least 3 phases: cyclic, biaxial, nematic, and ferromagnetic BC. So the interesting question arises as to which state fills which vortex core, and how can the vortex core be embedded in BC if the core and BC have different symmetries. I mean, those 3 phases have all different discrete symmetries. Therefore, it's not trivial, for example, how this vortex core can be embedded in this, or vice versa, because it's a different discrete symmetries. That's why we call this problem vortex tiling problem. So, as an example, let's consider the fractional vortex in a biaxial nematic phase. Biaxial nematic phase, by the way, to show you that this question is realistic, we know that the medium AT symmetrical field is on the border between this and this. So therefore we can play both phases. And consider now 1/2, 1/4 vortex. The meaning of this is that it has a 1/2 mass circulation and 1/4 spin vortex. The order parameter is simply like this. Then it looks like this. So as we go around the vortex, spin rotated by 2 pi over 2, and the gauge changes by pi. The question is that if the matrix BC is biaxial nematic, then which state fills the vortex core? What happens if we rotate this piece? The answer is the cyclic phase. This is a result of numerical simulation. Then the next question is how the cyclic core, which has three-fold symmetry, be embedded in the surrounding biaxial magnetic, which has a four-fold symmetry? The answer is this. So this threefold triad connects smoothly into the surrounding problem. So the vortex core looks like something like this, and the core has naturally threefold symmetry. What's the experimental consequence? As a result of this, vortex core undergoes spontaneous symmetry breaking into a triangle. So if you look at the vortex core of a biaxial nematic phase, then the prediction is that the vortex core has to be triangle. And this is, by the way, in a sense, very natural, because as I said, cyclic phase is a BC of trio singlet, and this microscopic structure is amplified into this macroscopically observed triangle shape as a vortex. So I think this is quite an interesting phenomenon.
Is this somehow related? I don't remember exactly, but wasn't in liquid helium that there was also some odd result by Saloma and others that somehow the vortex core could deform and
actually there is one essential difference. So one example is a double core vortex in liquid helium stream predicted by Warwick Bucks. And double core vortex, the origin of this core deformation is a disintegration of an integer vortex into a pair of half quantum vortex. This is energetics. Since originally one vortex is disintegrated into two pieces, so the core is naturally elongated. So this is what is called double core vortex in liquid helium stream. In this case, this triangular shape is rather intrinsic to this tracing. So
does this have an effect on the vortex dynamics? I mean, presumably now the bending, the energy difference you get by bending the vortices depends on how they're oriented, is that right? Rather than being like cylinders, they're like rods with threefold symmetry. I mean, it would be easier to bend them in some directions.
You mean the structure of a vortex?
Yes.
I guess.
Do you see that in simulations?
It's twisted, as I will show later. Okay. So there are actually real experimental implications because this vortex styling can be implemented in F equal to the medium BC. So just prepare F equal to the medium BC, and prepare initial state is 1, 0, 0, 0, 1, and rotate the systems. Then you will get, for example, in any magnetic sublayer, perform Schrödinger experiment and look at M equals 0 component, then the prediction is that it has threefold symmetry. So this is a very clear telltale signal.
What's A30?
That's a trio singlet. As I said, trio singlet. So this is the amplitude of trio singlet. So for example, this is the amplitude of spin singlet tail. And this is the amplitude of trio singlet here. Trio singlet. So this is a theoretical logic. We can calculate. And this is something experimenters can observe. Okay, so as I mentioned, this can be observed by just preparing the initial set, this like this, and rotate in rotate these systems. And there are many different types of vortex styling problems depending on the initial configuration. So as I mentioned, if the initial configuration is 1, 0, 0, 1, which experimenters can choose, then we get this. But the initial condition can be chosen as 1, 0, 0, 1, 0, 1 over square root of 2, 0, 1. This is the cyclic phase configuration. Then we have, then the matrix is cyclic. So matrix is 3-fold symmetry, but vortex core is biaxial nematic, which has 4-fold symmetry. Therefore, in this case, the vortex core is a rectangle rather than a triangle. And depending on the type of vortex, we have different symmetry breaking as a vortex core. And this is the answer to the question. So actually, the vortex core is 3-fold symmetry, and vortex is twisted, something like this. And this is what we call twisted, rotate, something like this. Looks like a break. And what happens if we connect this twisted like this? Then we have a new topological object called vortex. Unlike the U1 vortex, which this bottom has two quantized circulation, one along the vortex rim, one around the vortex rim. And because of the two-fold quantized circulation, this object is topologically stable. How to create this? I still have yet to answer. This is a theoretical. But the point is that this is stable. Okay, so
why do you say it's stable? Just because it's just because it has a non-zero topological. You mean it's not homotopic to a vacuum solution? You mean it's not homotopic to a vacuum solution? I mean, saying something's topologically stable, I don't know what that means. There are lots of models where you have topological charges but no stable solutions. I mean, things can collapse. So I'm asking what the phrase topologically stable means.
This has two circulations. So if there is only one circulation around the ring, then it collapses. It can collapse. But in this case, since there is also a circulation, non-zero circulation around this.
So I think this point is that this object we discussed in charged condensates a lot, and this objects were discussed in charged condensates. He is expert on these things.
Yes.
And so essentially by this quantization, this insert quantization, it's still in general case can shrink to zero. So it doesn't have energetic stability. I think this is what the question is.
Yeah, all I'm saying is just because it's topologically non-trivial doesn't necessarily mean that it's going to be stable to collapse.
Am I right that basically what you're asking is that since the object is local and if we go away from the object we see essentially nothing, it can shrink into the point. Right?
Yeah, exactly.
Because the net charge is zero. If you look locally, we see a vortex line, but it's finite, meaning that it is topologically neutral.
No, that's topologically it is. So it's like a P3. So this topological charge is not mostly, but it can. So having non-trivial topological charge like this does not prevent against shrinking it to size small.
Well, it might do, but it's an issue. You need to know what the energy. You need to know what the free energy of the system or whatever. You need to know something about the dynamics of the system. Just the topology of the field space and the configuration isn't enough to conclude that it's going to be stable.
Well, what we have checked is via the numerical simulation. There is no such shrinkage for this case.
Okay.
Yeah.
But did you add, say in a superfluid, just in a U1 vortex, we know that if you have just zero temperature, it keeps going by Kelvin theory. It's a dynamic property. But if you add, say, normal component, thermal excitations, it goes and shrinks and collapses. So if you add, say, excitations, so if your initial state contains, say, phonons, not just the ground state, not the zero temperature, but phonons, probably it will collapse.
Yeah.
Because the underlying order parameter is U1. So this U1 manifold cannot hold two different types of fiber.
But what's wrong with it? Holds at least one. So and it still collapses because my point was
that is a case where only one circulation exists.
There is no global topological change. Globally, this guy is topologically neutral.
This is
globally. If I go away from this guy, I see nothing. Am I right or am I wrong? If I go away, so if this guy is 1 centimeter and I'm going 1 parsec from this guy, do I see it?
Let's see.
Maybe I'm missing something, but my feeling is that I will see nothing.
No. Actually, there is. Because suppose that we consider this axis, then since there is pi 1 around this, so this gives rise to a non-zero circulation around this axis, however far away you go.
But the question
No.
is whether you
It's then I have to take a counter. It's a very, by the way, this is the reason why Feynman was, as he explained to us a few days ago, why Feynman was thinking that a roton is a vortex. It's a prejudice. When you go away from a vortex, you see the structure of the field. This is just a dipole field, which can be created just by a moving object. Because they have a prejudice, like, and basically you're just giving the same argument. Well, if we look at the vortex from the distance, which is much larger than its radius, without having a counter which goes, because it's fine-tuning, if my counter goes just right into the ring, it's fine-tuning. If I have something which goes away from my ring, I cannot distinguish between the field created by a vortex and just a dipole field. So it's a very important point, by the way. I will discuss it slightly tomorrow, because I see that it's important. Because people keep making this mistake, just thinking that you can see a vortex, like a vortex pair, say vortex anti-vortex in 2D, or a ring from a large distance. You can never tell that there is a vortex or something else. You just see something, but you don't know whether it's a moving object or a vortex.
Unless you go to the core.
Yes, exactly.
Maybe to your question, I can say that in this case, order parameter manifold can have two non-trivial pi simultaneously.
Two
Non-trivial pi homotopy. Yeah, topology in this case is classified according to pi 1, the first homotopy group.
Yes.
Okay. And in the U1 case, there's only a single unique pi 1. In this case, there are two.
So you're saying pi 1 is Z2? That's what
No, pi 1 is not 2, but there are two pi 1s.
well, pi 1 of the vacuum manifold is Z2. It's Z cross Z. Is that what you're saying?
That protects this from shrinking.
Well, I don't agree with that. As I was saying, just because you have a non-trivial topological charge doesn't mean that things are going to be dynamically stable. I mean, if you take the Sturm model and throw away the Sturm term, or for the F-Hop model and throw away the quartic term, and put in something of non-zero Hop charge, then it will shrink and collapse. But it has, it has non-zero Hop charge. So
Well, actually, when the Hop charge collapses, then actually your order parameter space goes beyond what you have initially thought. And in other words, due to the dynamical instability, your initially assumed order parameter goes into a different order parameter space. If that happens, then the topological object becomes unstable. But that doesn't happen in this case.
Why does it in this case?
What is the way on this? No, well, let me say again. Okay. Protection by topology is guaranteed as far as your initially assumed order parameter manifold retains. But in the dynamical simulation, sometimes there is some dynamical instability which transforms your initially assumed order parameter manifold into a different one. Okay. In this case, topological objects can collapse. And I assume this is what you. Yeah.
Well, I don't know. That's a weird way of putting it.
So essentially, if you take this thing, so I think Martin is a mathematician. Let me try to formulate it in a more physical language. So essentially, we were studying exactly this mode, exactly the same objects, and also exactly the same nodes, but in a gauged models. So the main problem there is to avoid that if you have object with topological and trivial top invariant, yes, without gauge fields in the Gauss-Tepsky, etc., then its energy is roughly speaking proportional to its size. And then if you have finite temperature, then you can monotonically decrease decrease these objects until, for example, to the coherence length. And then your topology becomes trivial, you can get rid of the Hopf charge.
Yeah.
So essentially,
so that's the initial Faraday argument.
No, Faraday had no linear sigma model. All his objects were protected by infinite energy barrier.
Because of the Faraday.
Yeah, and because there was no equivalence of coherence length. Because otherwise so he had this nonlinear sigma model, any relaxation nonlinear sigma model would give finite energy barrier against eliminating it. Yes. And so essentially, but if you have something different from nonlinear sigma model, then if there is nothing, no things to stabilize textures on preferred size, then so essentially what Martin is saying, I think, is that by the fact that one has topologically non-trivial objects, it doesn't guarantee stability for the system which is not non-linear sigma model, essentially when you have any sign coherence length, because energetically it will always want to collapse to characteristic length scale where you lose this U1 cross U1 topology.
Yeah, I think we are saying the same thing. I mean, beyond the coherence length.
Yeah.
Okay. The order parameter manifold.
Yeah.
Is transformed into different.
Yeah.
Okay.
And without like gauge field or something, this will always want to this solution will always want to shrink to size smaller than coherence length. Is that the case in your system, or do you have some tricks to stabilize it? Except the dynamical propagation stabilization or something.
Well, I think one thing is that this is an energy conserving system.
Yeah, so zero temperature, and you have some you stabilize it by some momentum conservation, right?
No momentum conservation system. Yeah, but energy conservation system. Because this is a cross phase. Yeah, and as far as our numerical simulations are concerned, this approach is stable.
But I think also it wasn't like but in Sutcliffe didn't they have, so I think they studied numerically also in exactly Gauss-Tepsky two-component model, right? The same objects. Didn't they have to have some didn't they find some stability?
They certainly
had some critical density interaction with
they certainly looked at some ungauged version of the problem where they had skyrmions, effectively skyrmions, but I don't remember the details.
Masahito, did you do the linear analysis of this type of Bose-condensed state? That if you do the linear analysis, then you find the spectrum of elementary excitations, and the presence of imaginary or negative excitation energies tells you that you have either dynamical or energetic instability.
Right.
The dynamical instability is crucial. Energetic instability is something that if you have very low temperatures tending to zero, you may handle that.
In this case, I haven't done that. Yeah, I haven't done that. We have only checked via the numerical simulation. Okay, so I hope I have convinced you of the fact that Skinner DC offers various new phenomena in terms of quantum phases, magnetism, and topology. And we have new topological objects life modes, and the no variant vortices give rise to an interesting feature in terms of component patterns. And the vortex tiling problem predicts new topological objects and the new core deformation. This is all what I want to tell you. Thank you very much for coming.
Is there intuition that you can have for why the vortex core would want to be this, what is it, like a cyclic state, I guess, when you have the polar vortex? I mean, I guess you want it to be something other than polar so that you can remove the singularity, right? But I mean, it could also be like ferromagnetic. I mean,
So you mean why the core is
yeah, I mean, other than numerics, I mean, is there a kind of a qualitative reason that I mean, could it just be the spin-spin interaction and the vortex core would, favor?
Perhaps ferromagnetic has an axis symmetry, or the band is axis symmetry. Then maybe that cannot be commensurably connected to the surrounding object, because the surrounding object has a discrete symmetry. So it's very hard to plug in spherical symmetry into this.
Mm-hmm.
So the question was that since why this ferromagnetic core cannot be embedded into this present by actually.
Yeah, but which parameter that you put in? I mean, you just put in the Weberian numbers. So
in numerical simulation.
Yeah.
Yes.
Yeah. So, but if you, I mean, you are at the point at which that state is almost stable already. The cyclic state is almost stable already. Yes. So if it fits in the core, so it would have a chance. So, I mean, you are not at the point that it has a chance. I mean, if I tried on the other side, okay, I would bet that the ferromagnetic.
That's a good comment. So I mean, your question, your suggestion is that if we start from the parameter here.
Yeah, well, I think your outside is nematic, right? Your outside, the bulk state is nematic, right? Is that right?
Outside, yes.
Yeah. So then, I would try the one on the left.
So here.
Yeah.
Okay.
I mean, if you can fit, then that is the best one because it doesn't like to have an empty core.
Yeah, that's interesting.
Yeah. And I think that is the same physics that I think you are actually mentioned, because the helium-3 is exactly that one. So if the circulation allows, then you try to fit there. And with something would fit there, but depends on which one is more favorable.
Yeah. So Stanley's comment is, it might simply be elastic, because I took the number around. So if I start number around this, then this can be private.
So it might not be so, I mean,
Or
it might not be for every. You might have completely general, but for any pneumatic state, you always have a cyclic core. Right.
It might not be completely general. Yes. Yeah. I'll check this.
Questions? Thanks, Pierre.